Hello everyone, this is another video on statistical mechanics. Okay, where we'll be solving, where we'll be continuing our previous lecture, where we discussed about quantum harmonic oscillator. Okay, and here we'll be discussing about classical harmonic oscillator. Okay, this is done. So in this lecture, we'll be discussing about classical classical harmonic oscillator. Okay, okay, classical harmonic oscillator. So let's try. Suppose let's have a system. Let's have a system of n identical independent. I have told you what is the meanings of identical, independent, and non-interacting. Their meanings we have already done. Non-interacting, non-interacting, distinguishably, distinguishably placed, bonding, classical harmonic oscillator, classical harmonic oscillator. Okay, so you can see classical harmonic oscillator. First of all, their energy is what? 1D classical harmonic oscillator P square by 2n plus half kx. Right? See, since our harmonic oscillator here are placed distinguishably, are placed distinguishably. Okay, so partition function will be partition function will be Zn is equal to Z1 to the power n. Okay, Zn is equal to Z1 to the power n. So now your Z1 will be written as, so 1 by h to the power f integration q p e to the power minus beta epsilon dfq dfq. Okay, where is f is a what? F is your degree of freedom for 1D classical harmonic oscillator. This f is 1. Okay, 1D for 1D classical harmonic oscillator, harmonic oscillator, f is equal to 1. Okay, so let's put it, z1 is equal to 1 by h integration q p into minus beta e. Okay, this is the limits will be minus infinity to infinity. Okay, if you remember, we had done it in the one of the sessions. The previous session, I have told you 1D. If this is 1D Cartesian, 1D is there, so Cartesian coordinates will be used, and here your limits will be minus infinity to infinity. Okay, so minus infinity to infinity, it will minus beta e dq dp. Is that all right? Okay, dq will be converted into dx. Okay, so 1 by h minus infinity to infinity minus infinity to infinity into a minus beta epsilon dx dp dt. Okay, yeah. So your energy we just saw. What is our energy value? Energy value is this one, p square by 2 n plus 1 plus 1 by 2 kx square. So let's put it here, 1 by h minus infinity to infinity minus infinity to infinity e to the minus beta p square by 2 n plus half kx square dx dp. So if I separate them out a bit, minus infinity to infinity minus beta p square by 2n dt minus infinity to infinity e to the power minus beta half kx square dx. Is that alright? Okay. Now we just have to do the integration. Okay. Integration of e to the power minus alpha x square dx is root over of pi by alpha. Okay. So 1 by h, the integration will be root over of pi by alpha. In place of alpha there is what? Beta by 2n into root over of pi by beta k by 2. Is it alright? Okay. 1 by h pi by beta 1 by k by 4n. Okay. 4n goes up becomes 2. So 2 pi by h beta root over of m by k. Is it alright? Okay. Okay, yeah. See, h by 2 pi is written as what? H cut. So in place of here, I can write like this or not. So 1 by h cut beta root over of m by k. This is your z1. Okay. Now, if you tell me k is equal to m omega square is equal to k by m, omega is equal to root over of k by m. So root over of m by k is what? 1 by omega. So here I can put 1 by omega. 1 by h squared omega beta. Right? So this is the what? This is your z1. Z1 is 1 by h squared omega beta. Is it clear? Is it clear? Okay. So Zn is equal to z1 to the power n, that is 1 by h squared omega beta to the power n, then beta h squared omega. Okay. I can write it also as beta h squared omega to the power minus n z. Alright. So this is the partition function for classical harmonic oscillator. Okay, next is the internal energy. Internal energy U is equal to average of energy is equal to minus del by del beta of ln z, minus del by del beta of ln z is beta h squared omega to the power minus n. Minus n will go out, n del by del beta of ln beta h squared omega. So n by beta h squared omega into integration of this one, derivative of this one, sorry. Okay, so this one will be n by beta, right? And beta we know is 1 by kt. So 1 by kt goes up in kt. Is it alright? Now again, next thing is Helmholtz free energy. Helmholtz free energy. Helmholtz free energy. A is equal to minus kt ln z. So minus kt ln z is what? Z is a beta h cut omega to the power minus n. So nkt ln beta h cut omega. Is it all right? Again, you can from here you can calculate entropy minus del A by del T. Pressure minus del A by del B and mu minus del A by del B. Is it all right? Okay. Okay. If you let's calculate it then. Entropy is minus del A by del T of A, right? So minus del by del T of A is how much? nkt ln beta h cut omega. Your beta is 1 by kt. So minus del by del T nkt ln h cut omega by kt. Nk goes out minus nk del by del T of t ln h cut omega by kt. So minus nk ln h cut omega by kt plus t into kt by h cut omega, the derivative of this one, okay, into um, h cut omega by kt square, okay, minus now derivative of this one I took, okay. You do this one yourself, then only you will understand. Otherwise, you won't understand. kt t and this tt cancels. So only minus one is left. Okay. So minus nk ln h cut omega by kt minus one. Is it all right? So if we open it minus nk ln h cut omega by kt plus nk. Okay. This is a what? This is a entropy. This is your entropy. Now pressure del A by del B mt minus del by del B of A. A is what again? nkt ln beta h cut omega. See, there is no n and t are constant. So n and t are constant. There is no term containing v. V. So this is zero. Okay. Now your chemical potential mu del A by del L. There is no negative sign in mu. Okay. Dt. So del by del N of uh, what is A again? nkt ln beta h cut omega kt ln beta h cut omega plus, yeah, that's not that much only, I think. Yeah, that much only. Yes. So this is your mu. Okay. So next is an enthalpy. If I suppose calculate enthalpy, see, if you calculate Cartesian function, you can calculate everything from it. Okay. Just need to remember the formulas. Enthalpy is H is equal to U plus PV. Your power, see, sorry, pressure is zero. So just put pressure zero. So H is equal to U plus zero. That is H is equal to U, right? U, we calculated U before. That is nkt. So H is equal to nkt. Is it all right? Okay. Now CV is what? Del U by del T at NB. So del by del P of NKT, that is NK, right? NK. Hmm. CP is what? Del H by del P at PM. So del by del P of NKT. So this is what NK. Okay. Now gamma. Gamma we know is CP by CP. And if you see, these two are equal, right? NK by NK. This is equal to 1. Okay. Gamma is 1. Okay. So this is a what? Classical harmonic oscillator. Is done. Okay. Classical harmonic oscillator we have covered. Quantum harmonic oscillator, so harmonic oscillator also covered. Okay. These two are done. Next, give a heading. Magnetic system. It's very important. If questions come from this NCS and it came this year in December. Magnetic system in canonical ensemble. Okay, so right down here we will have some magnetic dipole placed in a uniform magnetic field pointing along z direction. Yeah. See, if it is not mentioned, write a point. If it is not mentioned that a magnetic field is along z, like magnetic field is along z direction, it is not mentioned in the question. So you have to consider it yourself. Okay. Yeah, it is always along z direction. You have to consider it yourself. Okay. Sometimes, wait a minute, sometimes see, H will be given instead of B. So replace B everywhere by H. Okay, simple point. Okay, okay, let's see. Suppose let's consider a system of n magnetic dipoles having magnetic dipole moment moment mu, okay, that are identical, localized, distinguishable, and non-interacting, non-interacting, practically static, practically static, and are freely orientable, freely orientable, and are placed in a uniform magnetic field, hmm, pointing along, as you know, it will be along z direction, z direction. That is, b vector is equal to b z cap. Okay. So again, let's write some points here. So n magnetic dipoles are here. Mu vector is the magnetic moment. These are identical. Identical means what? Similar physical properties. Okay, similar physical properties. Okay. Next, localized. That means we can trace them. Localized means what? Let's write. We can trace them, and hence we can distinguish them. Okay, distinguish. Okay. So Zn distinguishable, that means Zn is equal to Z1 to the power n. Okay. Now non-interacting, non-interacting. That means mutual interaction. There is no mutual interaction. That means what? I have told you again and again this thing. Potential energy is zero. Okay. Practically static. Practically static. That means translational kinetic energy is zero. Okay. Now freely oriented. The last term is freely. Just try to understand these points. Okay. Freely oriented. That means they can orient it in any direction. Okay. So these are the dipoles inside n number of dipoles inside the this container, and your magnetic field is along z direction. Okay. So first of all, whatever we have done so far, our main objective has been to calculate what? Partition function. Okay. So since these are distinguishable, partition function Zn will be Z1 to the power n, right? Right. So we have to find this Z1. Okay. Let's consider a single dipole. Okay. So dipole is placed in, but since, write it down so that you can understand it easily. Dipole is placed in magnetic field, magnetic field B is equal to B Z cap. Hence magnetic, hence hence dipole, magnetic dipole will interact with the magnetic field with the and interaction potential will be given as potential energy will be given as potential energy is equal to minus mu dot b. Okay, is it all right? Okay. Now there are two cases that are possible. There are two cases in which our dipoles can be two cases. Our dipoles can be classical or they can be what? Quantum mechanical, right? They can be classical, they can be quantum mechanical. All right. So in case of classical mechanical, for example, classical dipole. What do you mean by classical dipole? Quantum dipole. Classical dipole means what? In case of classical dipoles, okay, theta is actually continuous variable. Okay, that means magnetic dipole can be oriented at any angle with respect to magnetic field. But quantum dipole means theta is a discrete variable. That means magnetic moment will take some particular orientations only. Did you get it? You must have studied it in atomic molecular physics also, where this vector atomic model, where the orientation is specific. Okay, there are like this kind of orientation. That means it's a specific orientation. That means it's discrete. It's not like continuous orientation of these dipoles. Okay, so right now classical means continuous. Okay, in case of classical dipoles, theta angle theta is a continuous variable. Theta is a continuous variable, or the magnetic dipole can be oriented at any angle with respect to b, at any angle with respect to b. Okay, so this is a what? Classical dipole. What happens in case of quantum dipole? In case of quantum dipoles, in case of quantum dipoles, theta is a discrete uh, variable. Okay, that means mu will only take some particular orientations only with respect to the. With respect to the magnetic field, right? Yeah, yeah. So this is your quantum and classical. We'll separately we'll discuss them also. So first one is classical dipole. Okay. So as I said, theta can be anything. It's continuous. It can be anything between 0 and pi. Okay. So if you see, so this thing is making a solid angle, right? Like the orientation itself. is making a solid angle. You can imagine this thing. Imagine it as a cone or something like that. Okay, this is called a solid angle. So to find partition function, we have to consider orientations possible possible within a solid angle. Okay, so solid angle is your d omega is equal to sine theta d theta d omega d phi. Okay, so our potential energy is how much? Minus mu dot b. I can write as minus mu b cos theta. Okay, right. So to find potential energy, actually, we have to do what? Focus on all possible orientations, because the basic idea to find partitioning function is to consider each possible energy state, because partitioning function is summation I gi e to the power minus beta en. So we have to take every energy possible. Okay, so write the point. So to find potential energy, we have to focus on all possible orientations, because the idea, the basic idea, because the basic idea to find partition function, basic idea to find partition function is to consider each possible energy state. Okay, so let's write it down. Z1 is equal to integration 0 to pi. So 0 to 2 pi, this is for phi. 0 to pi, this is for theta. Okay, just for your understanding, I'm writing like this. Don't write like this. Then minus beta e sine theta d theta d phi. Now e is equal to minus mu b cos theta. Okay, so place in place of e, put this one. So 0 to 2 pi, 0 to pi e to the power minus beta minus mu b cos theta sine theta d theta d phi. So 2 pi 0 to pi e to the power beta mu b cos theta sine theta d theta d phi. Okay, now sorry. So the integration of d phi is 2 pi. Okay. Okay, now see, I can take beta mu b cos theta as something d. So here this derivative is what? Minus beta mu b sine theta d theta dv. So sine theta d theta dv by minus beta mu b. Alright, the limits will be what? Here if you see the limits, okay. So I can write as 2 pi, limits will be minus beta mu b to beta mu b. If you check it, it is what v dv. So 2 pi e to the power v The integration e to power v, and I'm sorry, this minus beta mu b is also there. Okay, okay. So minus 2 pi by beta mu b e to the power beta mu b minus e to the power minus beta mu b. Okay, so this is the form. If I divide to multiply to, if you see this is actually sine hyperbolic x minus 4 pi by beta mu b um, sine hyperbolic beta mu b. Okay, okay, I'm sorry. There is another minus here actually. This should be minus here, and the below one will be plus. Okay, if you check the limit, so this will be like this. Then another minus will go out. Minus minus plus 4 pi by beta mu b minus I took another common. Okay, minus another common. Now it's correct. 4 pi by beta mu b sine hyperbolic beta mu b. Okay, so this is a what exactly? This is a partition function only. But distinguishable particles is Zn is equal to this is Z1 to the power n. So 4 pi by beta mu b sine hyperbolic beta mu b to the power n. Yeah, this is your partition function. Now what is our next job? What is the next job? You try this internal energy, right? Internal u is equal to minus del by del beta of ln. This one 4 pi by beta mu b sine hyperbolic beta mu b minus sorry minus n del by del beta this one. So 1 by 4 pi beta mu b sine hyperbolic beta mu b and the derivative of the whole one. Derivative of this one. So minus n beta mu b divided by 4 pi sine hyperbolic beta mu b. Derivative of this one, take it. If you take the constants of 4 pi by mu b, so it will be like minus sine hyperbolic beta mu b by beta square, derivative of this one, plus 1 by beta cos hyperbolic beta mu b constants mu b. This will be the answer. Okay, this should be the answer. Okay, if I divide this sine h beta mu b in the inside, it will be 4 pi by cancel out. Maybe will be cancelled. So minus n beta, what goes inside sine hyperbolic. Okay, and then beta square sine hyperbolic beta mu b minus mu by beta cos hyperbolic beta mu b by sine hyperbolic beta mu b. Okay, so sine cancelled out, cos by sine is cot, so minus. Okay, let's take the minus out also. N beta, this is 1 by beta square minus mu b by b cot hyperbolic beta mu b. Okay, this is all right. Removes free energy. This is your internal energy. Removes free energy is equal to minus KTLN Z. So put the value of Z here. So minus KTLN 4 pi by beta mu v sin h beta mu v to the power n minus NKTLN 4 pi by beta mu v sin hyperbolic beta mu. Now is a magnetization new one. So M is equal to what? Minus del A by del B, okay, at temperature constant. So minus del by del B. B is a magnetic field. Minus NKT ln 4 pi by beta mu B sin hyperbolic beta mu B minus NKT goes out, so NKT del by del B of, don't write it as beta, okay, this is B, 4 pi by beta mu B sin hyperbolic beta mu B. So NKT this by 4 pi by beta mu B sin hyperbolic beta mu B derivative of this one. 4 pi by maybe take it out. Okay. Mu beta, sorry, mu beta. So minus 1 by t square sin hyperbolic beta mu B plus 1 by t cos hyperbolic beta mu B into beta mu. This is all right. So this is the way to calculate what magnetization. Now this thing 4 pi cancelled, mu b cancelled, sorry, mu beta cancelled, okay? Yeah. B is still there. So this B will go up. NKBT. The sine hyperbolic will be divided here. Plus 1 by B. This will become beta mu. This will become cot hyperbolic beta mu. This is alright. This is a magnetization. This is a magnetization. Okay. Next is the what? Isothermal magnetic susceptibility. Im is equal to limit V tends to 0 del n by del B temperature. So whatever you get as M, you just take the derivative with respect to B at constant temperature. You will get chi m. You will get chi m as I will just write the value n beta mu square by 3. Okay, same things again. Entropy. You can calculate entropy del A by minus del A by minus del A by del T. Pressure minus del A by del B, and chemical potential mu is equal to del A by del M, sorry. This way you can calculate all these things. This is alright. Yeah. Okay, this is your classical dipoles. In the next session, we will be seeing quantum dipoles. Right? Yeah. Okay, write some questions for homework. These are questions from the first chapter. Okay. A random walker takes a step of unit length in the positive direction. The probability 2 by 3 on the step of unit length in the negative direction with probability 1 by 3. The mean displacement, the mean displacement of the walker after n steps is option A 1 by 3, option B 1 by 8, option C 12 by 3, option D. Okay. Try this question at home. Number 2. Box of volume B containing n molecules of an ideal gas is divided by a wall with a hole into two compartments. The volume of the smaller compartment is B by 3. The variance of the number of particle in it is option A n by 3, option B 1 by 3, option C root n, option D into n by 3. Option number 3. There is a 1D lattice with lattice constant A There are some of the questions you should try. Okay. And I think it's much for this class. And the next session we'll be discussing about quantum dipoles. Okay. So stay tuned to the channel. We're discussing quantum dipoles. Okay. Till then, thank you for watching.